the first thing is about the speed. How to increase the speed. The bandwidth per chip, suppose, is double for every 2 years. So if you look at the list page, you will find that about 8 years ago, we have our switch. The bandwidth is only 640 gig. But now, this year, we already have the chip solution based on Broadcom solution. We can deliver the 12.8T of the bandwidth. So single chip, different bandwidth. You may find that the bandwidth is keeping double for every 2 years, right? But the challenge is that when the bandwidth is double for every 2 years, but our end customer, the space, the reserve for our switch box is still double? No, no way. So we always want to keep the same form factor per size. Say 1 RU, keep it simple, 1 RU. So if you look at the chip, you will find that still 1 RU, but the bandwidth from 640 gig, 1.28 gig, 3.2 gig, and now 12.8 gig. So the bandwidth, thanks for the chip vendors such as Broadcom, that can provide a very high bandwidth of silicon solutions. But from the system point of view, Quanta, QCT, our challenge is how to make the same form factor of the box, the size, but to well handle the power consumption, the thermal, without sacrificing the signal qualities. So this is a challenge for every switch vendors, and we did in our new generation of switches now. And the box for this one is a demo in our hardware demo area outside. So this is a trend about the data plan. Another trend is about the port speed, right? Since we want to keep the same form factor of the box with more and more high bandwidth, that means we want to keep the port speed even higher. So from this page, you will find out the third interface that is from 10 gig to 25 gig and even 50 gig by different kind of modulation technology, from NRZ to the PAM4. So the third the speed is about 2 by 2 or by 3 for every 4 years. Today, we are on the era of the PAM4 base per lane 50 gig. And our product is to deliver with 400 gig by putting multiple lane of the SerDes. So this is another trend about the port speed that create a lot of the challenge, especially to handle the signal quality on some certain level of quality of a PCB. And we don't want to put some extra component to increase the signal quality. Just keep the board simple, but still keep the signal integrity without compromising the quality. So this is a trend of the port speed. So that we follow this kind of a trend, we even lead the trend. So this page, just for your quick reference, our product line, while our current offering. So we adopt the Intel CPU for years, and our switch, we offer the copper and the fiber switches from different port speed, from 10 gig, 40 gig, 25 gig, 100 gig, and even the 400 gig. The box is just out of the hall on our hardware demo area, okay? And we deliver the pizza box, 1 RU, 2 RU, and even the chassis switches, okay? So the story behind today's breakout section is about the speed and the features. The speed is how to increase the speed without any penalty on the signal quality and the cost. So the first box I want to introduce to you guys, the first one is about the speed. This is our 400 gig switches. The name is T1932IX9, which can provide 32 ports of the 400 gig. And the transceiver type, the cage is follow the standard QSPDD. And the based on Broadcom switch Mac Tomahawk 3. And the CPU here we adopt is Intel ProDE. And we also support the BMC and the BIOS boot. So this is the our new generation of switches. And we still keep this box 1 RU height, standard width and height. And it also provide a redundant components such as the power and the fans. Okay. So this is the front view and the rear view. 32 port on the front side, and we even keep the AC power on the front side. So the end user can choose to plug in the power from the rear side or the front side. since we keep the flexibilities. And the redundant power fans. And to handle the thermal is always a critical issue. So we spend a lot of effort on the thermal, the heatsink, and a lot of technology to make sure that this box can really support the front to back airflow on certain conditions, 45 degrees Celsius. Okay. And the box is live demo outside. So we successfully development and bring up this box. Okay. So this is a story about the speed, 400 gig, and the bandwidth 12.8 T. So this is the industrial most most compact size of the switch box in the 1RU. Okay. Then the second product I want to introduce is about the router. But when we develop any new product, we still want to make sure that our product can follow some kind of the business models. So QCT, we start to develop the disaggregation solutions, the hardware and software disaggregate about 5 and 6 years ago. So we call the business model, we call it the white box, right? So we deliver our white box for some certain end customer, tier 1, tier 2, all of our customers. So we believe that the white box switch, the story will happen from data center to the telecom. We call the white box routers. So we do see some business opportunity about the white box routers talking on the telecoms. Okay. So talking about the routers, on this page, there are multiple segments about the telecom, the ISP networkings. And our current focus is on the core router, edge router, and aggregation routers. This is when Quanta that we migrate from the data center to the telecom. And our networking team that our first move is on the core, edge, and aggregation routers. So let me introduce our router product to you guys. The name is T7080 and the T7040. Okay. So based on the solution from Broadcom Jericho 2, we implemented the Jericho 2 based solutions. So the main feature between the switch and the router is that the Jericho 2 can provide the large table size of a routing and a large buffer, deep buffering. So this is a target on the MPLS edge, provider edge, and even the core router on the telecom spaces. And our role is to develop the hardware, and we are working with some certain software partners to enable the MPLS software on this particular product. So we call it the white box routers. Okay. And this box is also demo on outside, static demos. So there are two products on this family, the brothers. So provide the 40 portable 1G gig as a 1RU form factor, and 80 port 2RUs. And leverages the same silicon solution from Broadcom Jericho 2, and the control plane from Intel x86 CPU Bro DE, and the BMC, and the bus boot, and even we support the TPM as an option. Okay. Also, we deliver the 100 gig solutions. So we also put the gearbox to convert the PAN4 to the NRZ conversions. And on our solution, we also reserve the design for the external TCAM. So external TCAM is the knowledge-based processor which can provide large table size if needed, and also can provide interface for the telemetry interfaces. Okay. Redundant power, redundant fan, and 1RU and 2RU, two versions of product, and a target to support the NEPS level 3. That is very important for the US telecoms. Okay. So this is a key feature by the Jericho 2, by our product of the routers. So it can provide the 2,000 million packet processor rate, and also provide the programmable in-field programmable engines. So that means the programmability is also supported in these particular routers, and the debuffer. Okay. And this is the front and the rear view of our product. So if gentlemen, you have a chance, you can see and touch our box outside this hall. Okay. 1 RU and the 2 RU. And the 2 RU versions here, redundant fan and the power. The interior design, Intel CPU, Jericho 2. Chassis dimensions. Okay. And this is the summary page of the product I introduced today. So we have the high-speed switches, 400 gig base. We have the rich feature routers, Jericho 2 base, 1 RU and the 2 RU for different port configurations. And the target application is different. The 400 gig switch is targeted on the hyperscale data centers. The super spine, the aggregation switches, low latency, and quick. Okay. The router is targeted on the ISP, the Telecom, which needed a comprehensive routing, comprehensive feature of the data plane, and the programmabilities. So it's targeting the core router and the edge routers. So different in the market. So this is my presentation today. And secondly, I will also introduce the PLN, the primary PLN, the PLN from the Broadcom, the Tomahawk 3. Mr. Robin to do the quickly introduce of the solutions. Thank you.
So my name is Robin Grindley, and I'm a principal PLM for Broadcom in the core switching group. I focus mostly on data center switches. So today I'm going to follow on what Paul described and talk a little bit more about the chip that goes inside the box he just showed you, or one of them, the iX9, Tomahawk 3. So this is a full production 12.8 terabit per second switch chip. And let's jump in. So those of you familiar with the Broadcom products, within the core switching group, CSG, we have 3 different basic product lines. So we're segmented to look at different market segments here. Oop, I think my graphics disappeared. Okay, so the Tomahawk line is what we're talking about today in the latest flagship, the Tomahawk 3. This is focused on massive bandwidth for hyperscale fabrics. So Paul said speed, speed, speed. Absolutely true. This is like the Ferrari race car, okay? It's just designed to cram as much speeds and feeds as you can into a piece of silicon. Now that being said, I'm also going to mention power, power, power. Because the other problem is that data center operators, you know, when they describe a data center, the metric they usually use is, this is my 32 megawatt data center. That's how they call it, all right? It's based on power. They have a power envelope, and what they want to do is cram as much speed and performance into that given power envelope. So the Tomahawk line is focused on speed, but also on power efficiency. Other lines here are the Trident line, which is more feature-rich, has programmability in it, more versatile. And then the Jericho line, the DNX line that Paul mentioned in the other product, focused really on flexibility, massive scale programmability. So different and complementary product lines. So Tomahawk 3. This is now in full production. We just declared full production at the beginning of October. It's capable of 32 ports of 400 gig, or it also obviously supports legacy configurations. So 64 ports 200, 128 100, all in a single chip. Massive bandwidth. So again, speed is critical here. We are really focused on the hyperscale. So this market segment, the Tomahawk market segment, is really focused on getting the performance and with the latencies and feature set required for hyperscale cloud customers, okay? So looking at new workloads, new ways of data center architectures, such as AI, storage, and how these things are evolving. And then really providing a big jump down in terms of the OpEx and CapEx. So power, 40% less than previous generation, and cost significantly reduced. This chip was introduced at the beginning of this year. So the bleeding edge, 12.8 tera, introduced at the beginning of this year, first silicon, and we're now in production. Okay? So 9 months, we can get these chips out, and we can get them out the door and fully production qualified. This was shown a little bit earlier. In addition to getting the chips out and into production quickly, you'll see that the pace has actually picked up. Typically, there was a cadence of about 18 to 24 months between chip generations. The Tomahawk 3 is actually 1 year behind Tomahawk 2, our previous 6.4T chip. So we're accelerating, okay? We're bringing chips out faster at the next nodes, and we're getting them into production very, very quickly. And the pace of the hyperscale is what's driving us. You can see that the hyperscale customers want more and more and more. You know, an enterprise customer, maybe they want more features, but their density isn't increasing at the same scale as the cloud. So this means getting things out fast. This chip stayed in 16 nanometer. Jumping to a new technology node would have put the chip out further. So we had the challenge of keeping the same technology node, but doubling the bandwidth, getting 50 gig PAM4 in there so we could get the density. But execution, it's really about execution, reliable execution. What is driving all of this bandwidth? Well, many different things. There's the traditional data center traffic, right? You do your web searches. But obviously, AI, deep learning, is a new area, and it's bringing with it its own bandwidth and other requirements. So machine-to-machine communication, large radix and bandwidth. So trying to get to a flat topology. The traditional close network is fine for things that don't require low latency, but doesn't scale as well once you get to this kind of workload. Storage disaggregation. So the storage network itself, in addition to the regular data center, is going through a bit of a transition right now. NVMe, JBOFs, there's an architectural change going on right now, and so we need to move along with it. Tomahawk 3 allows that as well. If you look at the latency, if you had a traditional multi-stage CLOS network, you can collapse it. So what we mean is, instead of focusing on the individual switch latency, which is important, the bigger factor is every time you have to go through yet another switch, you are inevitably adding a large amount of latency to your overall transaction latency. So the biggest bang for the buck is to try and collapse the network, higher radix, higher density of port speeds, and by doing this, you can get down to the low latencies requiring for machine learning. In terms of the power and cost, so previously we had 128 by 100 gig boxes based on our Tomahawk chip a couple generations back, and this is what they would look like. It's a chassis with a backplane and a whole bunch of line cards. With Tomahawk 3, we can shrink it down to the 1 RU box that Paul just showed you. That's a lot of metal that's gone. If you look at them side by side, we're now talking about the same kind of capacity, but if you use metrics that are publicly available, you can go look these up on OCP, we're talking about power reduction of 75%. You don't need all of these midplanes. You don't need all of the drivers for the internal chassis structure. And a massive reduction in the system cost. Huge number of chips. You have to partition the problem when you use the other generation chips. Now you can consolidate into a single piece of silicon. All right. So in summary, what we've really brought to the table right now is a story of cutting-edge execution. Chips that we can get out very quickly at the bleeding edge of technology, whether it's PAM4 on the SerDes or the density, while keeping the power low, also required by our customers, and driving the product cycle, getting out to production quickly. So we were the first 12.8 tera switch chip shipping, and now in less than a year, in only 9 months, we are in full production. And this is our first Tomahawk line chip with 50 gig PAM4 and 400 gig E support. So we're driving that next step in the hyperscale evolution to 400 gig ports. And we are consolidating all of this technology and bringing it to market fast. And that's what the hyperscalers are demanding of us. All right, that's it. Thanks very much.